Hello everyone. This video is going to be covering the relationship between activation and inhibition. And also going to talk about modifiers of enzymatic activity such as inhibitors or activators. It's going to look at the relationship of classical inhibition equations and activation. And I'm going to present some templates that you can use in Excel for modeling your data, either inhibition or activation, and relate that to an equation I'm going to talk about here. This presentation relates to an article I'm trying to get published at the moment in PureGA. You can see the link there, comparing enzyme activity modifier equations through the development of global data fitting templates in Excel. And to get right into it, classical inhibition, when I'm talking about that, I'm talking about obviously enzyme inhibition, and enzyme inhibition is defined using the Michaelis-Menten equation right here. And this equation, well, there's all sorts of great videos on how this works and what it's about online, so I'm sure you can find it. But basically, what you're looking at here is a description of what happens to a population of enzymes and how they convert their substrate to a product. The rate V is equal to the concentration of the substrate divided by the concentration of the substrate plus the substrate affinity constant times the maximal rate of substrate hydrolysis, which is the Vmax, maximum velocity. So this equation describes a population of enzymes that you would be looking at, and you would be looking at the conversion of substrate to product by either measuring the formation of product or the decrease in your substrate. And where inhibition comes into this is when a compound gets into the system and stops the enzyme from doing its job. On the right here, you can see the two of the basic or classical inhibition models. The first one being competitive inhibition, where your enzyme is trying to get its substrate so it can hydrolyze it in a product, but there is an inhibitor which mimics the substrate somewhat in its ability to bind to the active site of the enzyme. This prevents the substrate from getting to the active site and therefore decreases the turnover of substrate to product. The non-competitive form of inhibition assumes that the inhibitor doesn't have to bind to the active site, but it actually somewhat turns off the enzyme. So when the inhibitor is bound to the enzyme, the substrate is no longer either recognized or it no longer is catalyzed into product. So the reaction that breaks the substrate or turns substrate into product is stopped in some form. And these forms of inhibition are defined with the classical inhibition theories. They were derived using reaction schemes, and you can look those up if you want. I think they are derived here in a few videos online. So competitive inhibition, you get this equation where you're basically multiplying your substrate affinity term from the Michaelis-Menten by an inhibition term, 1 plus I over Ki. The non-competitive, well, and this makes sense because in competitive inhibition, you're only actually supposed to be affecting the substrate affinity, so having it directly multiply into the substrate affinity constant makes a lot of sense. In the non-competitive, this form of the equation, you are affecting the catalytic rate of the enzyme, so you're actually turning the enzyme off. So in this equation, the inhibition term is directly affecting the Vmax. So as your inhibition enzyme population gets bound by inhibitor, you're turning off each one of those enzymes in your population as the inhibitor is bound to it. And then the mixed form here is an equation that is used to describe changes in both the substrate affinity as defined by the competitive and the maximum velocity at the same time, because you can have that happen where your system the inhibitor changes both the maximum velocity and the substrate affinity. So if you look at these equations, you have this common term, 1 plus I over Ki. And, well, except for in the mix, you have it's a little bit modified because you have two Ki's. You have an alpha Ki and a Ki, supposedly one for affecting the substrate, or the enzyme with no substrate, and one affecting the enzyme with substrate. So you have two different binding events, essentially. But generally in biology, you see this very common mass-action relationship, and it's exemplified by the Michaelis-Menten equation up top here, where you have your substrate over your substrate plus your Km. So this is a fractional binding term, really. And it's the exact same thing you see when you have a ligand binding to a receptor, where you have fractional occupancy. And it's even used in defining inhibition as well, where the simplest term or the simplest way of defining inhibition is defined using IC50, an inhibition constant where 50% of the enzymatic activity is inhibited. And you can see they all have this common form of your substrate or ligand over the concentration of the substrate plus the binding affinity constant. So this is KD, KM, IC50. They're all binding affinity constants, and they all are doing essentially the same thing. If you look over at the graph, this is what that represents. So your binding constant would be the concentration at which you have 50% bound. And if you want to think about that, you can just, we'll just use the fractional occupancy equation here as an example. And say you are at a concentration where your ligand is equal to the concentration of the KD. Well, I'll just assume that if we just use 1 as the constant, the numerical value for KD, and we then make KD and L equal to each other, you have 1 plus 1 over 1 plus 1, so 0.5 or half, 1 over 2, 1 half. So as you increase the concentration of your ligand or your substrate, this sort of thing happens, okay? So initially at very low concentrations, you have very few of your receptors or enzymes interacting with their target. And then as you get to the concentration of the KD or the KM or the IC50, you have about half of the molecules being associated with their target, or the biological molecules being associated with their target. And as you approach very, very high concentrations, you're sort of pushing this to close to 100%. You're going to sort of a plateau effect up here. So this would be your Vmax, and you're approaching. So if we were to mathematically consider that again with the fractional occupancy and say keeping the KD at 1 and then making the concentration of your ligand 1,000,000, it would be 1,000,000 over 1,000,000 plus 1, so that would be 99 point whatever percent, so almost 100% association. And this produces the classic hyperbolic curve that is found in most biological studies. So then you look at this inhibition term that's used to define inhibition of enzymes, and it's kind of weird because it doesn't look like any of these terms, but it doesn't provide any more information, and it's using the same terms. It's using the inhibit. So if you look at your inhibition, percent inhibition here, it's using concentration of inhibitor over Ki, which is Ki is a binding affinity constant between the inhibitor and the enzyme. So this is a little bit puzzling. So anyways, so this provides a bit of a problem because this term, well, it's a little bit confusing. Well, maybe just for me. Maybe it's good with a lot of people. But this, it's sort of division in where it's put in these equations. So as you can see in the competitive, it's found in the bottom here, and it's found in the bottom here as well. For the competitive, it makes sense because it's multiplying into the km, so directly affecting it. For the non-competitive, it doesn't really make that much sense because it's supposed to be directly affecting the Vmax. But I guess because these terms are segregated, it seems to work well. It seems to be doing that. But these equations, they describe very limited forms of inhibition, and if you recall from the previous slide, they describe very strict situations. So the competitive, the inhibitor binds to the active site of the enzyme. The non-competitive, it affects the Vmax, but it can bind anywhere. But these are known as sort of complete inhibition equations in that they kind of produce an on-off effect. So specifically with the non-competitive inhibitor, as your population of enzyme is bound by the inhibitor, each one of those is turned off. So it's either working at its regular catalytic activity or it's off. So it's in an on or off situation. So the percent of the population bound with the inhibitor directly relates to the percent inhibition you see with the inhibitor binding to the enzyme population. This has led to the derivation of more equations. Specifically, you have to start thinking about what happens if your inhibitor binds to the enzyme, but it doesn't quite turn it off. It maybe produces 50% inhibition. So if you're talking about non-competitive, it binds somewhere, but the substrate still can interact with the active site, but it's just reduced in its affinity for doing that, or the rate at which it gets cleaved or it gets transformed from substrate to product is reduced. So to deal with this, more reaction schemes have been generated, and there's been the production of more equations. Just an example of a few: partial competitive, partial non-competitive, partial mixed non-competitive, and they're described in more advanced enzyme kinetic textbooks. However, if you look in the literature, specifically in drug development, most of the drug development out there sort of defaults to the use of IC50 values. So that equation from the previous page here, where your percent inhibition of your enzymatic activity is related to the concentration at which you get 50% inhibition. And this is a very minimalistic way of looking at how these molecules interact with the enzyme. But it has its benefit. I mean, because if you are developing a drug and all you're interested in is just that drug will stop the enzyme from doing a job that's producing some sort of disease state or medical condition, then you can shut off with this drug stopping the enzyme. It doesn't really matter what form of inhibition is taking place as long as you're getting the end result you want. So that being said, there are in the literature, and actually even at places like the FDA, the acceptance of IC50 values, well, they accept IC50 values either for publication or for submitting information for drug applications. So anyways, getting back to the inhibition constant, While I said before it's a common term, it really isn't a common term in these equations. In competitive inhibition, you're looking at this term multiplying into the substrate affinity value. In non-competitive inhibition, you're dividing your maximum velocity by your inhibition term. And in mixed non-competitive inhibition, well, you have two inhibition terms, and these relate to binding of the free enzyme or binding to the enzyme substrate complex. And so I have a few problems with that, mainly because it assumes that you need two binding events for you to affect either substrate affinity or maximum velocity. But anyways, that's a little bit more in-depth, and we'll probably make another video and talk about that later on. But anyways, to sort of understand what this term actually means, you can focus on the non-competitive inhibition equation. And if you actually rearrange it, you see the mass action inhibition binding term sort of come out here, where you now have VA max being multiplied by 1 minus the inhibitor over the inhibitor plus the binding affinity constant of the inhibitor to the enzyme. And this term becomes very useful because you can then just multiply your Vmax into it, and you get this term where you see Vmax minus itself times the percent of the enzyme population that's bound by an inhibitor. So as the percentage of the enzyme inhibitor population increase, or as the percent of the enzyme in your population is bound by the inhibitor, as that increases, you have a equal decrease in your Vmax. So it's a direct relationship of when enzyme binds an inhibitor, it gets shut off. However, you can easily modify that and make your second Vmax term into a delta, so a changing term, that being where your delta would be your initial Vmax minus a secondary value. Now, if at this point you can see that I've changed it from inhibitor to now X, which I'm going to refer to as a modifier, because if you were to make V2 bigger than V1 in this situation, then you're actually going to be describing activation, okay? And if you were to make your V2 value equal to your V1, the binding is not going to actually affect the activity of your enzyme population. So, and then if V2 is smaller than V1, you're going to get varying degrees of inhibition, right down to where V2 equals 0, then you're going to have complete inhibition, which is what's defined by the non-competitive inhibition equation. So this term is very useful for modeling increases or decreases in enzymatic activity of your population. And the same sort of term can be used to define changes in your substrate affinity, so you can model increases or decreases in the substrate affinity with this term. And you can pop them into the Michaelis-Menten equation, and you get this equation. So to sort of visualize how that equation works, we'll start again with the Michaelis-Menten equation here, where in the Michaelis-Menten equation you have two forms of the enzyme. You have free enzyme and you have free enzyme bound by substrate, and as your substrate concentration increases, the percent of the enzyme population bound with substrate increases, which is described by this mass action binding association term. So when you think about adding a modifier, either an inhibitor or an activator to the situation, you then have 4 different forms the enzyme can be found in the most basic model. You could there are more complex models, and you can start to think of what would happen if the inhibitor doesn't bind to the enzyme when there's no substrate, or what would or it binds differently when there's substrate versus when it's not. But if you just consider one interaction, you're looking at there being enzyme binding with substrate, enzyme binding to your modifier, and then enzyme binding with modifier and substrate at the same time. And in those situations, the catalytically relevant ones, the ones which are converting substrate to product or not, if the inhibitor is a complete inhibitor and completely shuts the enzyme off, are these two, the ones that have substrate associated with them. So if you were to look at this in a graph form, this is a graph just representing the 2 different binding isotherms for the substrate on the y-axis and the modifier on the x-axis. And I'm using percent bound or percent association values along each axis here. So for substrate, the first row would be 0, and then 25% association, 50, so equal to the substrate affinity constant, the Km, 75 and 100. Same thing for the modifier along the top. And I'm using the percentages to describe the concentration or the percent of the enzyme population which is associated with the substrate, and the percent that would be associated with the substrate and the modifier. So you would have, so if you look at 25% association, say, of substrate and enzyme, you're going to get, with no modifier, you're going to get 25% of the velocity of your Vmax. However, if there's a modifier present, and say we'll go with 25% association of the modifier, then you're going to have 18.25% of your enzyme population working as normal with the enzyme substrate. And you're going to have around 6% in this form, so working at a different substrate affinity and a different catalytic rate. So that's all this equation really is describing. So this here is basically defines the percent bound, which would be these values, and this substrate, the Km, are basically right here. So moving right along, how can this equation be used to model data, and how does it compare to the other equations that we've been talking about, the other inhibition equations? Well, to address that, I've developed a global data fitting process in Excel, and that's in the publication that this is related to this presentation. And that'll let you take your data, or whatever data you find, and pop it in, and globally fit it to all the classical inhibition equations and this modifier equation. And I also have a secondary template where you can actually even model your data using the partial inhibition equations, and I'll be showing that shortly as we get a little bit further into this. So historically, we did not have computers, and we didn't have data fitting for the biochemists who were looking into characterizing inhibition in these systems. And so there was a development of graphical methods. Probably the most prominent being the Lineweaver-Burke double reciprocal plot, where you're plotting the reciprocal of the rate, or 1 over V, versus the reciprocal of the substrate concentration. And this produces a linearization of the Michaelis-Menten equation, and allows you to determine your Vmax and your Km values based on their intercept on the x and the y value axis. So what that looks like, this would be a representation of competitive inhibition, where you can see there's an intercept on the y-axis. This represents no change in your maximum velocity, and the change in the Km is represented by the intercepts on the x-axis changing specifically. And here's the representation of the non-competitive, where you can see there's no change in your substrate affinity, but in this example, the change is in the maximum velocity of your reaction, which you can see is changing the intercept on the y-axis. And this is actually still used today. This is probably the most common way you'll see inhibitors represented and classified in publications. And this is data. This is actually from an information data set produced by one of the companies that makes equipment for measuring these doing these sort of studies. And in it, you can see that they're doing just this. They're doing a Lineweaver-Burke of the enzyme hydrolyzing different substrate concentrations, and these are their data points. And then they're doing a linear regression best fit line through the data points. And they're getting an intercept at the 0 value here, approximately at the 0 value. It looks a little off, but at the 0. And they claim this is a competitive inhibitor. And well, that's, as the title suggests, pattern recognition. So they're acknowledging that they have an intercept here on the y-axis, and they have changing intercepts on the x-axis. So they called this inhibitor competitive. So this was taken from biotech's application note. This is this is used to instruct researchers on how to analyze their kinetic data that they get from their system here. And so there's not really any reason why this data shouldn't be competitive. If you look at it, they're in this application they're measuring this system, so they have a substrate which is being cleaved by their enzyme into two products, and this is colorful, so they're able to measure the formation of this over time. And they're using a substrate mimic as the inhibitor, so you can see clearly how this looks very much like their substrate that they're using, their chromogenic substrate, except that this is not converted into anything by the enzyme. It just blocks the active site. And so the big question is, does this data actually conform to the competitive inhibition model, or the classical competitive inhibition model? Go now to the template I've developed for looking at this. So I'll just do a quick go through on what this template does, and then we'll look at the data from that note from biotech, and we'll look and see if it actually does fit to competitive inhibition. So if you want to fit your data and look at what model it conforms to, you can take it and you can just drop it in here. So the first part of this spreadsheet is just basically for you to drop in your substrate concentrations. So you can have up to 15 substrate concentrations if you like. And you can have up to 15 inhibitor concentrations, so you can do repeat at up to 15 different inhibitor concentrations, and this should be a lot more than anybody really needs. And the first row here, you would put your rates for that you observed at each substrate concentration when you don't have any inhibitor. And you can put in more than just one row of zero inhibitor. You could make this 0 as well, or as many as you like, and it will just model all that. But the first one should be 0 because that data is then used by the template to generate an initial guess of the Km and Vmax based on a modified direct linear plot. These plots were developed by Cornish-Bowden, but if you want to see it, these other tabs here are basically just the fitting of the data, but the summary page has all the plots on it, so you don't really have to look at those, but you can if you like, if you want to see what the thing is doing and how this is all linking together. So the initial thing it's going to do is it's going to use these two rows here to estimate your Km and your Vmax. It's going to show plots of that. It's going to have your raw data, and it's going to have a line going through it so that you can see that it's fitting well. And then as an initial estimate of your Ki, or your inhibition constant, it's going to take the inhibitor concentrations along this line and the initial substrate concentration, the change, and it's going to do a linear guess as to where approximately 50% inhibition is, and it's going to put this here. I mean, this doesn't really mean all that much. It's just to provide an initial guess as to what the Ki might be for your fitting down here. So this table contains the models that the template you can apply your data to. So you can use a non-competitive, competitive, uncompetitive, mixed non-competitive, and the modifier equation, which I was describing earlier. And then here are the parameters of each of these equations. So you have your Km and your Vmax, which is standard for all the Michaelis-Menten based equations. And then for your non-competitive, there's only one Ki value. Competitive, the same, one Ki value. Uncompetitive, you have one Ki value. Mixed non-competitive, you have your Ki and your alpha Ki values. And for the modifier equation, you're going to have a second Km value, a second Vmax value, and a Ki value. All right. So the initial values that will appear here will be the Km and Vmax values from up above, and the Ki value estimated here will appear here, and these are just guesses as to what might possibly happen. They might be completely wrong, and any of these values you can easily just change by hand. You don't have to rely on the values that are here, and you can just run your fitting again, changing these manually to see how good of a fit you can actually get. And that's actually advisable because usually when you're doing these sort of fittings, there's the possibility that you're going to get stuck in local minimums, and you're not going to get the best fit the initial time. So you should probably do a fit initially, copy and save those values, and then just put in new values, make up some new values, put them in, and try it again and see if you get a better fit. So next off, okay, so anyways, so it has the parameters here. Now it has the sum of squared residuals. The residual is the difference between the calculated value and your experimental value. They're usually squared because when you're fitting an equation, if you have positive and negative values, the negative values are going to cancel out the positive values, and you're going to get an improper fit, because sum of squared residuals are used to determine how good your fit is between your equation and your experimental data. But once I put some more actual data in here, maybe it'll be more apparent as to what's going on. You also have relative standard error being calculated, and Bayesian interference coefficient, BIC. This is a value that scores fitting of equations, and it's used to discriminate between equations, which one fits better. And these are all color coded, so it'll show you which one is fitting the data the best near the end. Also, right below this is a box plot. This box plot is of the residual values, so the difference between the calculated and the experimental values. This time it's not squared though. This shows you the distribution of your residuals positive and negative 0, because if your calculated values equaled your experimental values exactly, there would be 0 residuals, so there would be just a dot at 0. But because there's going to be some that are positive and some that are negative, this is a way of visualizing the distribution of your error around 0, and it's a way of comparing the fit between the equations. You'll see some that have a big distribution of residuals, positive and negative, and you'll see some that are very small. And all the values used in the generation of the box plots are found here on the right. So you have your minimum, maximum, median, first quartile, third quartile, and I'll show that again when we get to put some data in here. And down below there's a summary of the fit for each of the equations. So the first one, and it mirrors the order of the table here. So the first one is non-competitive, and you're going to have your equation, you're going to have your parameters, so your Km, Vmax, Ki, and you're going to have your sum of squared residuals. There's a line wave work plot, a regular velocity over substrate plot, and a correlation plot up here. A correlation plot is the experimental versus the calculated values. If they are all equaling each other, you should have a relationship very close to 1, slope of 1, and very little distribution of the, or very little variation of the slope from 1, and the R squared for the distribution along the best fit line should be very, very small. Followed by competitive inhibition, uncompetitive, mixed uncompetitive, and the modifier equation. And the other plot here, 1 over V versus inhibitor concentration, is known as a Dixon plot, I believe. I sometimes forget, but anyways, that's just another way of visualizing the data. So I've already fit this data. This is actually the first example in the paper that I talk about, but I'll just grab the data here to show you what happens when you would input your data into the spreadsheet. So just grabbing the data, you would place it here, and automatically you get the generation of your Km and your Vmax value. So this is the modified direct linear plot, and the intercept here produces a median value for estimating Km and Vmax, and you can see that the predicted equation for using Km and Vmax goes through the experimental data very well. So that would be using this Km and this Vmax, producing a line based on the Michaelis-Menten equation through this data. So these two here. And you have your estimation of your Ki based on these values here. So now you can see that as a starting point, the Kms have all jump to here, the Vmax is here, and your KIs as well. And it actually provides, based on these values, it shows which one is fitting the best initially. So the dark green is the smallest value with the RSS. So this says that non-competitive inhibition is, based on these values, is the best fit here, which is mirrored by the BIC and the standard error. And if you look at the box plot, you can see how these things, the residuals look, this being 0 here. Hopefully they all line up by 0 after we do a little bit of fitting. And you can go down and you can look at how the plots look at the moment. So this is a correlation where if the experimental and the calculated equaled each other, they should all line up on a line, and the slope of the best fit should be 1, and the R squared should be close to 0.9 something. And then you have your Lineweaver-Burke plot showing that right now it's a very poor fit. The calculated values do not fit to the experimental very well. Same with the direct velocity versus substrate, and Dixon plot also showing a terrible fit, and that's mirrored in all of these. So to produce a fit in this, what you want to do is you want to use the solver function in Excel, and the solver function is found under data. It's not installed initially. You have to go into the add-ons and add it on, and there's a lot better explanations of how the solver works in other videos, I'm sure, and I'm sure you can look that up. But this is a nonlinear regression algorithm, and how you're going to use it with this template is you're going to set your objective. So in this case, if we wanted to fit to the non-competitive inhibition equation, we would start with the squared residuals would be our objective. We want to minimize that. So you would go through it, you would say we want to minimize or go to a value of 0. You're not going to get to a value of 0, but tell it to go as small as possible. And then you're going to say, I want you to minimize the sum of squared residuals by changing the variables, and the variables in this are the parameters. And in this case, you should probably start out with the inhibition constant. Okay, so we'll just run that and see what happens. So we have an initial RSS of 1 to the positive 3. Just say OK, and now you can say it went from 1 to the 3 to 4 to the 2. So 1,000 to 400 now is what the RSS has changed to. So it's obviously gotten quite a bit smaller, and we'll see what the distribution looks like. And now you can see that it's actually starting to look very nice. The median value is very close to 0, and it looks like an even distribution of the whiskers on either side. And you can, this here, actually these dots here are the residual dots themselves. So while this is a representation of means and maximum and minimum, these are the residuals here themselves, so you can take a look at them. And if you go down, well, you can see that this has changed. It doesn't look all that great still, but you'd probably want to actually rerun it, and this time you're going to not just focus on the Ki, but you would focus on using your Km, your Vmax, and your Ki at the same time, and solve and see what we get this time. And now there's more of a change, so it went from 400 to 300, and if you go down, the plot is starting to look even better. So correlation between your experimental and calculated looks, well, you're getting a slope closer to 1, and your residual or your R squared value is around 0.9, which is pretty good, and you can see that it's doing its best to try and fit this equation to this data, but seeing as it's was identified as a competitive, it's not very likely that the non-competitive equation is going to be able to model this data. But anyways, let's go to the actual fitting and see what you can get out of this. So yeah, after going through and fitting it all, this is what I came up with, and I mean, these are the minimum values I found. People might be able to get better ones. You're welcome to try it. The paper is online, and you can open up this this data set and you can play with it and see if you can get a better result. But you can see that after fitting to all the equations, the best fit that we got out of this was using the modifier equation. The non-competitive and the competitive equations both provide a fairly decent fit based on the residuals, or the squared residuals, and based on the BIC values and on the relative error as well. So if you go down, you can then look at how these equations, once they're globally fit to the data, what they look like. And you can see the non-competitive really does not provide a very good fit at all for this data. Moving on, you can then look at what sort of fit you get with competitive, and you can see right away that the correlation is much better. You have a slope of the correlation plot of 0.998, and you have an R squared of 0.9915, and you can see that the fit is very good for the for modeling the non-inhibited data. So this top line here is the non-inhibited data, and this is the first inhibitor concentration. But once you get to the higher inhibitor concentration, it looks like it's doing a good job here in the substrate versus velocity plot, but you can see that it's not doing a very good job once you look at the Lineweaver-Burk double reciprocal or at the Dixon plot. You can see that it's not really doing that great of a job. And then you can look at, well, here's uncompetitive, which obviously does not fit this data very well at all either. And then you have mixed non-competitive, which fits almost as well as, I think a little bit better than competitive, but similar results. You can see it seems to fit very well in just the direct plot, but in the double reciprocal, you can see that the high inhibitor concentration doesn't really fit with this data. And you can see that with the modifier equation, you actually get a little bit of a better fit. You can see with the double reciprocal, it's lining up with all of the points. All the points are going to be connected here in the Dixon as well as in the direct plot here. And the correlation plot looks very good as well. So does this data conform to the classical competitive inhibition model? Potentially, but the model that the modifier equation does seem to produce a better fit. So if you look through my article, there is actually a second template, and then with that one you can model your data sets against the partial equations, so partial non-competitive, partial competitive, partial uncompetitive, partial mixed non-competitive, and you can basically evaluate how your data or any of the data sets that are in the paper fit with any of these equations. And hopefully it's helpful for some of you. But the big question I think to bring up at this point is, what's the point? Because I've already said earlier on that a lot of people are disregarding a lot of these equations now, and they're moving on to just using IC50s for characterizing drugs and submitting articles. And well, This equation, the modifier equation that I described here, was not just developed for single substrate interactions. It was developed to model more complex systems. And this is for understanding systems that are a little bit more complex. And I'll probably do a video on this again in the future, or in the future at some point, where you can actually expand this modifier equation out so that you can describe substrate interactions where you might have substrate activation or substrate inhibition, and then you can, in a modular way, add on interactions with drugs or with modifiers of the activity. In previous publications, I've used this methodology to describe the inhibition of cholinesterases. Cholinesterases are important in Alzheimer's disease. One of the big drug targets, and understanding how drugs interact with the cholinesterases in their different forms as the substrate takes them from either a substrate inhibited to a non-substrate inhibited, and how the drugs interact with each of these forms is an important thing to study in understanding more complex biological interactions, which are probably key in understanding disease at this point, because the oversimplification where you're going back to IC50, it means that you're just looking at one substrate concentration and you're not considering multiple different forms of enzyme and inhibitor and how they interact and how these things are working at a biological level. So I hope that these templates are useful for people, maybe people who just need to find some way to model their activation, or want a good way of looking at characterizing their inhibitor. And hopefully it'll open up, allow people to expand on some of the things I've done and model more complex interactions as they get more comfortable with modeling these equations in Excel, or using these equations in Excel. And I'm probably going to do a video based on how you can take almost any equation you find in the biological literature. So like maybe we could open up one of these textbooks and just take a couple of equations and put them in Excel and show how you would model them and show how you would fit it to your data, and do a step-by-step progression and show how you don't have to just rely on the equations I put here. You can actually do whatever equation you want, and you can even modify the templates from this paper to include other equations if you like. Well, anyways, thank you very much for watching, and I hope that this is useful for a few of you.